Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So we were talking about in the previous lecture the dynamic optimization problem, which involved taking decisions over n time steps or n time periods. So the time periods were denoted in this way: 0, 1, 2, and so on, ending at a terminal time n. We were taking decisions for each time period, and the decisions when were to be, we had taken this example where we were taking decisions for an inventory control problem. So the decisions were being made at the left hand point of the time period, and noise was being realized at during the time period. And because of the presence of noise, we saw that our problem, which was actually stated as first as having to decide the actions that we need to take at each time instant, that problem actually became a problem about planning for every possible state that could be realized during this time instant. So so to recall, say suppose xk is the state at time k, uk is the action at time k, xk plus 1 is given as fk of xk, uk, wk, where this is wk is the noise at time k or during at time or a period k. And the problem was to minimize this cost, which was a sum of a terminal cost plus 0 to n minus 1 plus costs at each time instant. Now, this minimization was to be achieved by choosing actions at each time step, but because the plan had to be made before the realization of uncertainty, our way of posing the problem was that of minimizing this over all policies. Policy is denoted by mu 0 to mu n minus 1. Now, we notice that this would become therefore a function of the policy and also of the initial state. Okay, the cost that we would incur would be a function of the policy and the initial state, and so the optimal cost was the cost of the optimal policy. This was denoted by j star of x 0. So notice that this optimization, the one that I have put in a box here, this optimization is an optimization of a function over the space of functions. Okay, the decision variables is a sequence of functions. So so what one needs to decide is this sequence of functions. Now, just imagine, suppose for simplicity, suppose there were just suppose there were 10 states at each time instant, 10 states say at each time instant. Suppose you had 5 actions to take, 5 possible actions, 5 actions that are admissible at each time instant, and suppose there are say 3 time periods. Okay, so you want to do this, you want to make these decisions over over 3 time periods. So, this needs to be decided thrice, right. So, how many possible functions are we looking at? So, how many choices are there for functions at the first time period? So, a function at the first time period would map the set of actions to the set of states to the set of actions, right. And so, for every state you can take 5 possible actions. So, as a result, the number of possible functions that you can have at time instant 1 is 5 raised to 10, right. And now, you have 5 raised to 10 possible functions at time instant 1. Similarly, there are 5 raised to 10 possible functions at time instant 2 and 5 raised to 10 possible functions at time instant 3. So, the total number of choices therefore becomes 5 raised to 10 times 5 raised to 10 times 5 raised to 10. As you can see, this is an enormous number just for a simple problem like which involves 10 states and 5 possible and 5 actions and 3 time periods. As the number of time periods increases, as the problem gets more realistic with more states and more actions, the number of possible choices grows even further, right, it grows even larger. So, consequently, thinking of this problem as in the space of functions is intimidating. It's practically impossible to solve the problem if you want to think of the problem in terms of functions. So, our goal is going to now be to see if we can somehow get to the value of the function implicitly, either through this by somehow cleverly evaluating the function only at relevant points, or somehow getting to the value of the function through by optimizing not over the space of functions, but over the space of actions in some way. Okay. So, at the cornerstone of this reduction is what is called the principle of optimality. Okay. This is what is called the principle of optimality. The principle of optimality in dynamic programming simply states the following. So, let me state the actual principle and then I will explain what it means. So, it says this. So, let pi star, okay, which is just denoted by mu 0 star to mu n minus 1 star. Suppose let this be an optimal policy. Be an optimal policy for the dynamic programming problem for the dynamic programming problem that we have stated on the left. Okay. And we will make a technical assumption and assume, okay, the technical assumption is assume that when using pi star, a given state xi, so denoted xi, occurs at time I with positive probability. Okay. Suppose it occurs at time I with positive probability. Now, consider the following problem. Consider the following, let us call it a sub problem. Okay. Consider the following sub problem where we we are at xi at time I and want to minimize the cost to go from time I to time n. Okay. So, consider this sub problem where suppose it is as if your decision problem has actually started at state xi and at time I. The original problem has actually started at time 0 with state x0, but we are not looking at that problem. We are looking at a sub problem which has started at time I and form a nominal state xi, okay, and it continues from time I till time the original time horizon that you had fixed, which is the end till time n itself, right. So, the cost then is the cost that you would incur from I up till time n. Okay, this is what we call the cost to go. Okay. So, the cost to go is expectation, you still have the terminal cost g n of x n and you have this cost which starts from k equal to I and goes till k equal to n minus 1, once again of now g k x k. Okay. Now, x k and u k remember is going to be evaluated as a function, u k has to be evaluated as a function of x k as before. Okay. So, this now looks like any other dynamic programming problem except that it has started from it does not have time horizon n, but time horizon n minus I, all right, and it starts from state xi. Okay, then now here is so here is the our result. So, the result is that the truncated policy, then the truncated policy and that is denoted by mu I star mu I plus 1 mu I plus 1 star till mu n minus 1 star, right, is optimal for the above sub problem. Okay. So, what is this principle of optimality saying? Let's go through this carefully. So, the principle of optimality is basically saying this. So, suppose your pi star, okay, is the optimal policy. This here is your optimal policy. Okay, I am going to take this as my optimal policy. Okay, and it says suppose I do the following. I consider a sub problem. Okay, consider this sub problem in which you start at state initial state xi, okay, at time I, okay, and we want to minimize the cost to go. You want to minimize the cost that you incur starting from time I going up till time n. Okay, this is your cost to go. Then if you look at this particular problem, okay, for this problem, what is the optimal policy? Well, the principle of optimality says you just look at your original policy, this original policy that you had here, and just truncate it. Look at the truncation of this policy. So, this policy has functions for each time instant, right, from 0 to n minus 1. You look at the policy starting from time I till n minus 1, all right. So, look at this a truncation of this particular policy, and that is your truncated policy mu I star to mu n minus 1 star. Then that truncated policy is actually optimal for this sub problem. Okay. So, this policy, so what is this effectively saying? So, let us think about what's in plain English, what is this problem, what is this the principle of optimality actually say. So, let us suppose we think of a problem of finding a shortest path from going from say Mumbai to Delhi. Suppose you want to find the shortest way of getting from Mumbai to Delhi. What is the what would be and suppose you found the shortest path, that means you found your optimal policy, which says that you take go to this town, then you go to that town, and so on and so forth. Say, and you find that the optimal path from going from Mumbai to Delhi, say, passes through Jaipur, say, for instance. Now, what does this principle of optimality say? Well, if you have found the shortest path from Mumbai to Delhi, and suppose that path passes through Jaipur, okay, then you look at the leg of your shortest journey, which has gone from Jaipur all the way till Delhi. Then that leg should also be optimal for the problem of finding the shortest path from Jaipur to Delhi. Okay. We were not really looking for solving the problem of from Jaipur to Delhi at all. Okay. But if your shortest path passes through Delhi, all right, then the optimal thing to do, then the optimal path that you have found, the optimal shortest path that you have found all the way from Mumbai to Delhi, has to also be in this leg, has to also give you in this leg the shortest path from Jaipur to Delhi, right. This is the principle of optimality. Now, we have encountered something like this in shortest path problems in linear programming and so on. But this being a stochastic problem is a little bit more general, because here it is not as simple as just the shortest path passes through so and so point, because the states that you will end up in, or the cities that you will end up passing through, etc., depends on noise. Okay. And so what we need to do is put in a few qualifiers, which is what we have done here. We need to put in a few qualifiers about the occurrence of a state with positive probability, right. So, we said that we can say this for states that do occur with positive probability. But once they occur with positive probability under the optimal policy, what we can be sure is that starting from that state till the very end of the time horizon, the optimal policy continues to remain optimal, or the truncated version of that optimal policy continues to remain optimal, right. So, what this means is that your way of solving, your way of thinking about dynamic programming can be broken down a little bit. So, we do not need to think of this as finding these n functions mu 0 to mu n minus 1 all together, but rather we can think of this in chunks. Now, chunks does not mean that you think of them separately for each time period. That is not the goal. The goal is not to separate out or remove the interdependencies between time periods, but rather we think of it starting from one time till the very end, and then starting from some time I till the very end, and then move that time I backwards. Okay, that would be the way by which we would approach this particular problem. So, I will elaborate on that in a moment. So, this is essentially the principle of optimality. So, let us see how we can employ this for our inventory control problem. So, what is the principle of optimality? Well, we can think of the principle of optimality is saying, well, whatever policy you start off from, that policy will continue to be whatever policy is optimal for the entire problem will continue to be optimal for any for the problem starting at any time I till the very end. So, why do not we look at the extreme version of this, which is that you put I as n itself or as n minus 1 itself. So, you start from the tail of the problem and you work backwards till you get to the initial time instant. So, let us see how that works. So, this is now dynamic programming. Principle of principle of optimality. So, this is principle of optimality now applied to inventory control. So, suppose we are at so let us start from the tail sub problem and tail sub problem of length 1. Okay. So, tail sub problem of length 1. Now, this is actually, remember, not just one sub problem, it is actually n sub problems, multiple such sub problems, because if you see, there is a sub problem here where for each xi, right. So, you have a sub problem for of course, you have fixed the time instant now as n minus 1, but you have also the state to be decided, and that here is notional, it is any any given state xi, right, at time I. So, we need to do our calculation starting from any initial state xi. So, suppose at the beginning at the beginning of period n minus 1, the stock of the item is x n minus 1. So, you have x n minus 1 units of the item. Okay. So, now clearly does not matter what has happened in the past, the inventory manager should now order the amount of inventory that minimizes the cost that starts from now till from time instant n minus 1 till the very end. So, what is the cost then? So, since you are starting at time instant n minus 1, the cost that you incur is the cost of ordering, etc., which you incur at time, cost of ordering, storage, whatever is so R of x n minus 1 and C of u n minus 1. So, the cost associated with that time instant and the terminal cost associated with time instant n, right. So, the inventory manager has to simply look at these two terms, which is the cost in that time period, the n minus 1th time period, and the terminal cost. Okay. So, he clearly the optimal quantity to order is the solution of Now, remember we had, so you want to minimize this. Now, remember we are now at time instant n minus 1, and we are given that we are starting from some initial state x n minus 1. So, for us now this x n minus 1 here, this term is not a random variable anymore, right. So, this is given to us. So, this is actually deterministic. Technically what we have here is actually not this, but rather given x n minus 1. Okay. So, given x n minus 1, this is actually deterministic. Likewise, u n minus 1 is to be chosen as a function of x n minus 1. So, this quantity is also deterministic. Okay. So, this optimization is now simply a vector optimization, although there is an expectation here, we are not optimizing over functions. So, all the randomness involved is actually present in x n, and that is because x n itself is equal to x n minus 1 plus u n minus 1 minus w n minus 1. The w n minus 1 is the random term, right. So, this actually becomes minimization. So, I can actually take out a few terms here. So, firstly this x n, the term that depends on x n minus 1 here, this is just a constant, additive constant, it has no effect on my optimization. So, I can just drop this term, right. So, this is, and likewise this being deterministic, will actually come out of the expectation, right. So, putting everything together, what I am looking at is minimizing. So, okay, let me. So, putting everything together, what we are looking at is minimizing r x n minus 1 plus the minimum over u n minus 1 of c of u n minus 1 plus the expectation now of capital R of x n minus 1 plus u n minus 1 minus w n minus 1. This is given x n minus 1, right. So, now let us denote this particular thing here as a and since remember we want to order a non-negative amount always. So, this is to be constrained in this sort of way. So, this was our constraint on the action, right. Okay. So, this particular thing, let us denote this by a term, let us call this j n minus 1 of x n minus 1. This here is the, so this gives us the, what is this particular thing? This is giving us the optimal value, okay, the optimal cost that you would incur if you started from state x n minus 1 at time n minus 1. Why is it the optimal cost? Because after all you have taken the optimal decision you could have taken if you were to start from x n minus 1. So, starting from x n minus 1, the optimal thing for you to do would be to choose an action u n minus 1, okay, and the action u n minus 1 would be the one that minimizes this particular cost, right. So, this here is so this is what's this here is called the value function. At time n minus 1. So, what we have got is the value function at time n minus 1. So, now naturally this is a function of x n minus 1, and the reason it is a function of x n minus 1 is because we said we will we started off our calculation saying let the stock be at some level xn minus 1, some nominal level xn minus 1. So, naturally the optimal cost you will incur starting from that period onwards is the optimal cost you would incur starting from that level onwards is a function of xn minus 1. Right. Now, let us look at tail subproblem of length 2. Right. So, okay, before I mention tail subproblem 2, notice what we have got here. Of course, what we have got here is the optimal value of starting from any state xn minus 1 that you could potentially reach. But in addition to that, we have also got what the optimal action you would, the optimal action to be taken as a function of that state, right. So, the minimizing the minimizing u n minus 1 here, this here, when we are doing this, the minimizing u n minus 1 actually gives you the optimal action as a function of x n minus 1. So, for the nominal x n minus 1 that you have chosen, the optimal action is the minimum, is the minimizer here, the argmin here, right. So, u n minus 1 star actually implicitly is giving you is implicitly coming out is implicitly being received as a function of x n minus 1. So, this dependence here of the optimal solution to the parameter x n minus 1 that we have chosen, x n minus 1 was the parameter, u n minus 1 is star is the optimal solution. This dependence through this defines for you the function mu n minus 1 star, and it will turn out that this is actually also the optimal the leg of the optimal policy or the component of the optimal policy for the overall problem, right. So, what we are getting is through implicitly here we are getting the value function, and also in the process of calculating the value function we are obtaining also the optimal inventory policy to be chosen from that time onwards.